Hello, calculus friends. This is AP Calculus 5.5 and 5.8 review. The last page of our review packet here, we are given the following integral, the integral from 0 to 8 of 5 divided by x cubed plus 2 dx. And we are asked to estimate the value of this integral using 5 different methods of approximation. Left-hand endpoints, right-hand endpoints, midpoints, trapezoidal rule, and Simpson's rule. Right? And basically the only two new ones here are the trapezoidal rule and Simpson's rule. But before we do any of these approximations, I just want to take a few minutes to set a few things up on my calculator just to make this problem easier for myself. Okay, so grabbing my graphing calculator here, the first thing that I'm going to do is in y equals, I am going to put in my function, which is 5 divided by, and then I need a parenthesis for my denominator, and my denominator is x cubed plus 2. So x to the third power, arrow out of the exponent, plus 2. Okay, and there I have my parentheses around it. Okay, so here's my function. And I know that I am looking at this integral from x equals 0 to x equals 8. So for my window, I have x equals 0 as my x min. I'm going to change my x max to x equals 8. I'll leave my x scale at 1. I'm going to leave my y minimum at 0 just because I happen to know that this integral lives above the x-axis the entire time here. And then my y maximum I'm going to change to, I don't know, let's do 4. Okay? And let's take a look at the graph here. So this is what our function looks like. Okay, so all of the area from 0 to 8 is going to be above the x-axis. Therefore, we know that all of the answers that we get for our integral approximations should be positive, right? Because all of our area is positive or above the x-axis. Okay, now because I have entered in my function into y1, what's really nice about that is I'm going to be able to use the table feature when I'm trying to find the values of my function for my left endpoints, my right endpoints, and my midpoints. So that's another benefit to taking the time to take a look at the graph. Okay, so for my first example, I'm going to be estimating the value of the integral using left-hand endpoints. So if we take a look at, and they tell us to use n equals 4 also, right? So 4 rectangles, left-hand endpoints. So if this is our x-axis here, 1, 2, 3, 4, 5, 6, 7, 8. Okay, and we're looking at left-hand endpoints. First of all, we know that if we're only going to have 4 rectangles, then our delta x is going to be equal to, remember it's going to be b minus a, so in this case 8 minus 0, divided by n, which is the number of rectangles, which is 4. So we end up with 8 divided by 4, or 2. So we know that the base of each rectangle, or our delta x here, is going to be 2, right? And so, you know, we can sort of envision that we have rectangles here like so. And if we are doing left-hand endpoints, then we know that we are going to be taking the y value of the function on the left-hand side of the rectangle. So I would say that my L4, right, my left-hand rectangles, 4 rectangles approximation is going to be equal to my delta x times. And then, again, if I'm taking the height of the function on the left-hand side of the rectangle, then, you know, wherever my function is, I'm going to be looking at the value of the function at x equals 0, at x equals 2, at x equals 4, and at x equals 6, right? Because I might have something that looks like this, and those are where my heights are going to come from. So I need to find f of 0, f of 2, f of 4, and f of 6 for my left endpoint approximation. So I know that L4 is going to be equal to, my delta x is 2. Now I'm going to go back to my graphing calculator, because remember, I put the function in y1, so I'm going to use my table feature. So second level table, rather than plugging all these numbers in, And you remember, you can just type right over the top of these. I want to know when x is 0, 2, 4, and 6, what the value of my function is that is in y1. So 0. I should have started with 0. Let me go back. So 0, 2, 4, and 6. Okay, so right there, I have the values that I need for my equation, 2.5, 0.5, 0.0758, and 0.0229. So I'm going to go ahead and I'm going to plug those into my equation here. So 2.5 plus 0.5 plus 0.058 plus 0.0229. Right? And then I just have to do the math. Add those together, multiply by 2, and we get that our area approximation with left-hand endpoints is going to be 6.197. In problem number 10, we're doing the exact same thing, except this time we're going to be using right-hand endpoints. So if I were to re-sketch my graph really quickly here, just so that we can consider our x-axis. Okay, and again, our delta x is still 8 minus 0 divided by 4, so our delta x is still going to be 2. And our rectangles are still going to live from 0 to 2, from 2 to 4, from 4 to 6, and from 6 to 8. Except that this time, when we find our right-hand rectangle approximation, we're going to be looking at the value of the function on the right-hand sides of the rectangle, right? So it's going to look something like this. So we know our R4 is going to be equal to delta x times our first approximation is going to be at x equals 2, right? So this time it will be f of 2 plus f of 4 plus f of 6 plus f of 8. All right. Well, 3 of those we already had from our last problem, so we can just go ahead and plug those in. Again, our delta x is 2. Our f of 2 was 0.5. Our f of 4 was 0.0758. Our f of 6 was 0.0229. And now for our f of 8, I'm going to go back to my table on my graphing calculator, and I'm just going to hit 8 here, x equals 8, enter, and that value is 2.5. Wait, sorry. I was looking at x equals 0. My apologies. That value is 0.0097. Okay, so 0.0097. Okay, grab your calculators, add those together, and multiply by 2, and we get that our right-hand 4 rectangle approximation for this integral is going to be 1.217. Wow, quite a difference there between the left hand and the right hand approximations. So in this case, I would assume that L4 is giving us an overestimate because our function is decreasing, and R4 is giving us an underestimate because our function is decreasing. Okay, so now let's take a look at our midpoint rectangles and see what we get with that. We should expect that our result from the midpoint rule should be somewhere between what we got for L4 and what we got for R4, right? So again, taking a look at kind of our y axis here for our problem. 1, 2, 3, 4, 5, 6, 7, 8. There's our x-axis. And again, we have our rectangles here from 0 to 2, from 2 to 4, from 4 to 6, and from 6 to 8. Our delta x is still 8 minus 0 divided by 4, so our delta x is still 2. But this time, if we are trying to find our midpoints, So we're finding M4 here. This is going to be equal to delta x times, but this time the midpoint of the rectangle is going to be where the height of the rectangle is going to be at the x value right in the middle of the rectangle, right? So we're going to be looking for our heights here at 1, at 3, at 5, and at 7 for our heights of our rectangles. So it might look something like that. So we need f of 1, f of 3, f of 5, and f of 7. So I'm going to go back to my table and my graphing calculator, and I'm going to type those values in. So I want x equals 1, x equals 3, x equals 5, and x equals 7. So I can see when x is 1, I'm at 1.667. When x is 3, I'm at 0.1724. When x is 5, I am at 0.0394. And when x is at 7, I'm at 0.0145. So I'm going to go ahead and transfer those values onto my paper right now. So I know my midterm approximation with 4 rectangles is going to be equal to 2 times. And then f of 1 was 1.6667. F of 3 was 0.1724. F of 5 was 0.0394. And f of 7 was 0.0145. Okay? Adding those together and multiplying by 2 gives us a midpoint for rectangle approximation of 3.786, which is what we would expected. This value is between L4 and R4. Now, just because I'm curious, what is the exact value of this integral? Well, again, let's go back to our calculator, because remember, with FNINT, we can calculate exact values of integrals. So I'm going to go to second level quit, which is going to take me back to my math screen here. And then under the math key, number 9 is our FNINT. So I just have to type my integral in here. I am doing the integral from 0 up to 8. And then I need to type in my function, which is 5 divided by, now I need a parenthesis here again, x cubed plus 2. X to the third power, arrow out of that, plus 2, close that parenthesis, and then this would be dx. And I hit enter, and I get that the exact value of my integral is 3.7697, so I would round this to 3.770 for the AP test, 3.770. So we may want to jot that down. The exact value of the integral from 0 to 8 of 5 over x cubed plus 2 dx is equal to 3.770. So we were pretty close with our midterm or our midpoint approximation to the actual value of the integral.